right, so tomorrow we're going to have a recitation related to homework 3. And I suppose we received all homework 2 already? Or it was due today? Almost all, okay, all right, that's positive. All right. Because I offer an extension and there will be no more extensions of that now. All right, so there will be a recitation regarding homework 3. And one of the things we haven't discussed is about projects for the class, okay? Because you start working, so you don't go the last week and you say to me, my project is literally 3 days before the presentations, okay? Because then I really get mad. And I think if, in some sense, you don't feel the need to have a project, it's a good thing to know so I can give more homework, right? I mean, it's one or the other. So projects are good for you because it gives you an opportunity to integrate things with your research and learn something new. And I want simple projects, by the way. You know, in other ways, if you take a paper from the literature in this area and you implement what it says, the application examples, that's fantastic. That's a project. Something we haven't discussed about. So that way, when you give a presentation to the class learns something new. I mean, that's the whole idea. So it's not a way to do nothing and then pretend here's my project, okay? That's not very good for yourself, for me, and for the university. All right. So may I suggest that within like the next week or so, you come up with an abstract for your project, okay? And this time, you won't be able to change it. So make your abstract with at least one reference, so I know that you're bounded by something. Okay? You missed the most important analysis for the class. All right. So we discussed the sum product algorithm for factographs, and you know, there were a few more slides left on the last lecture that is now posted because I realized we forgot to post it the same way we forgot to post the videos. All right, take notes. So we need the videos posted. So today what I'm going to do is I'm going to move past the sum product algorithm and discuss first the Max-Sumn algorithm, and I will discuss what that is in sort of very general terms. Then I'm going to actually take a step backwards, if nothing else for historical reasons, and give you a few slides on something that is sort of a subset of the sum product algorithm that we did for photographs that is called belief propagation. And at least you need to know when you hear it, because people talk about belief propagation, it's basically a subset of what we already have done. But I wanted to just cover it in a few slides so you see the notation coming from people that are grounded in information sciences, sort of a different perspective of what we have done up to now. And assuming we have time, I'm going to start to discuss another exact inference algorithm for general graphs that is called the Junction tree algorithm. I am not going to give you all the details, some sort of simple examples. And then when we come back on Tuesday, I will provide some of the details on the different versions of these algorithms. And hopefully you can do one of these implementations in your homework. By the way, once we cover these things for maybe the next several lectures, we're going to go backwards and do examples, for example, for hidden Markov models, for state space models. So we're going to try to revisit these algorithms in specific context. So in some sense, you have another month or so to go back to these notes and read them again, okay? Because we will revisit them on specific examples. All right, so let me introduce this Max-Sumn algorithm and what the problem is about. So obviously in probabilistic graphical models, we have modeled the joint probability distribution of many random variables. And we figure out how, given some evidence, we compute conditionals and marginals and things like that. So right now, let's say we have a graph to represent a probability P of X, and we want to find the value, the maximum of x that maximizes this p of x, and also that maximum value of p of x. So if you think of p of x being the posterior, you're maybe asking, what's the value of x that maximizes the posterior, and what is that maximal value? Okay? So the difficulty with this problem, all right, is that if you maximize marginals, what you will get if you put all the x's together is not the same x's that will maximize the joint distribution. And here is sort of a trivial example. We have binary variables x and y. These are the corresponding probabilities for these variables to take the values shown. You can see the value of the probability of x equal to 0 is 0.6, the probability of x equal to 1 is 0.4, y equal to 0 is 0.7, and y equal to 1 is 0.3. So x, the argument of x that gives you the maximum probability for the marginal is x equal to 0. Right? We agree? And the maximum, the value of y that maximizes the marginal of y is y equal to 0. But if you look at this table, this is basically the joint probability distribution of x and y. The maximal happens when x equal to 1 and y equal to 0. Not the same values. Right? So, I mean, this is one example, but you can generalize this and you can see that you have to be very lucky where the x's that maximize the marginals are the same as the x's that maximize the joint. So what we need to do is we need to find an algorithm that we can do this with the same efficiency as doing inference in graphs. All right, and that algorithm is called the Max-Summ algorithm, and in principle looks identical to doing inference in graphs. All right, minus some small perturbations. All right. I had mentioned that lots of these algorithms, really they're very common in in dynamic programming. So some of the things you'll see today, they will also look like dynamic programming. So let's say this is our graph, this is our evidence node, this is a bunch of nodes we don't really care, and this is the query nodes. All right, so we're interested to compute, when we did inference, to compute the probability of xf given xc. And the whole idea of the sum product algorithm is to do sort of these summations in an efficient way on the graph. So right now we want to find the xf that maximizes the probability of xf given the evidence, which is basically the same as the probability maximizing the joint, because if you write this, the joint divided by the evidence doesn't make sense. So this is the same. So effectively, this slide says if you have evidence or not, it doesn't matter. You can treat the problem of finding the x that maximizes the joint or this probability for evidence accounted basically the same way. All right. So in this case, I mean, you can put xt to the given values and still you have the joint distribution and maximize it with respect to xf. All right. Now, the reason that we will be able to extend the inference algorithms to do this max algorithm has to do with the fact that the operator max distributes over multiplication. The same way we saw, with the summation when we did the inference algorithms. So, for example, this is what we took advantage to push summations inwards, when we did elimination algorithms. And you can see the same thing is applicable when you have maximization. So the maximum of AB and AC is the same as A times the maximum of BC. And this distribution of the max operator over multiplication will allow us to do sort of the same sort of idea that we did with elimination when we were pushing summations inwards, so we can do less algebra than doing all of them simultaneously. So if you have, let's say, some factorization that involves x1, x2, and x3, functions of the three, and you want to find the x1, x2, x3 that maximize this product, obviously you can start pushing some of the max operators inwards. I mean, in this case, of course, it is trivial because H, I did not put any x1 or x2 here, didn't put anything else here. So, but obviously you got the spirit that somehow we will be able to push this forward. Okay. So here is the simple chain problem that we have seen everywhere. Undirected graph, let's say we define this, these are the maximum clicks, so we define this with a potential psi 1, 2, psi 2, 3, psi n minus 1, n. So if you want to find the x that maximizes this, so effectively what you will need to do is write this maximization operation the way that you see on the bottom. Okay? So this is what the whole algorithm is going to be, but you will see there is sort of a little complexity that we need to be able to account for. So here you are going, x10 appears only on this term, so you can actually do this maximization. Then you will get something that depends only on n minus 1. So this combined with the previous potential, you can do the maximization n minus 1, etc., until basically you can do a maximization here with respect to x1. All right, so let's do an example, and actually if you understand this example, you understand everything in the picture for this Max-Sumn algorithm, and I call this elimination algorithm, and actually I copy the plot from one of our earlier lectures where we were eliminating first x6, then x5, x4, x3, x2, and x1. So in this case, we want to find the maximum of the joint probability of x1 to x6, but I take here that x6 is evidence. And as we said before, it doesn't really make any difference, okay? So this is a directed graph. So this is the exact factorization, nothing special again. P of x1, x2 given x1, x3, x1, x5, x3, x6 given x2, and x5, x4 given x4 given x2. What is x4? x4 given x2, okay? And then I put delta, an evidence potential there to fix the value of x6 at x6 bar. Okay. So we start pushing the maximization inwards. So we see first what terms involves x6. And there is this times this potential. That's the only thing that involves x6. So we can actually find the maximum of this with respect to x6. But when we say we're going to find the maximum of this with respect to x6, this is for all possible values of x2 and x5. Because you notice in that function, x2 and x5 are arguments. They're not given, right? So, I mean, there's some function of the three arguments, okay? So x2 and x5 are arbitrary here. So when we maximize with respect to x6, we have to do it for all possible values of x2 and x5. It's very important. Okay, not for one value, for all possible values. Okay? So you do this maximization, and the same way we did with elimination, we're going to call this H6, because 6 is the node we eliminate, and the arguments are x2 and x5 that are left. So you're going to have to compute this maximum with respect to x6, and we call it a function h6, x2, x5. We did the same thing with elimination, but in elimination, what did we do to x6? So we sum it out, right? We marginalize it. Here, we don't sum, we max. Okay? All right. Then we have to look at all the terms that involve x5. Obviously, there was this term from the original distribution times this new potential h6. So again, the three arguments here are 3 and 2, so that we will get a new function that is called h5, because 5 is eliminated of x2, x3. Then we need to eliminate on, to maximize on x4. This function will be let's see, we said to do it on x4, right? So this function, we're not playing it all, it's only this blue thing that you see here, all right? So this will be a function of x2 only, which is h4 of x2. Then we need to maximize on x3, which will involve this argument plus this function h5. This is what you see here. This is h3 of x1 and x2. Then we need to maximize on x2 everything that has x2, which is this times that times this h3. We call this function h2 of x1. And then we're done because we only have a function of x1. We can maximize it, and that will give me, will give me something, a value. And that's the maximum of this probability. Okay? So, so in many ways, there is nothing very different from the elimination algorithm. Okay? But there is something this process here doesn't say anything about. So we computed the maximum of this probability, but if I ask you, what is the value of x1, x2, x3, x4, x5 that maximize that joint probability, what are you going to tell me? So this calculated the maximum of the joint, and now I am asking you, what are the values of x1, x2, x3, x4, x5 that together they maximize this distribution? So I want you to look in the blue areas there and try to think what the algorithm is going to be that you will see 10 slides from now, and it will look more confusing in those 10 slides down the road, unless you actually understand here how you're going to do it here. Let me ask the following. If you look, so in this case, right, we eliminate, let's say, from the leaves all the way to the root. So let's call 1 is the root, okay? You can do anything you want, but the way we have done it in this elimination sequence, x1 is the root. So do we know the value of x1 that maximizes this distribution, the joint? Do we know the value of x1 that maximizes this distribution? Notice what in the last step, this problem, right, has only one argument here, which is x1. So do we know x1? Can we compute x1? Yes. So can you tell me now, looking at this, how are you going to compute x2? Or what do you need to do in this calculation to allow you to compute now the value of x2? You remember when we computed this, when we performed this maximization, for what values of x1 we did it? For one value, for two values, for what value of x1 did we do this maximization with respect to x2? It's in the definition, you can see it. For what value? When we maximize with respect to x2, right, x1 is there, it's an argument. So what did we use for x1? Huh? Nope, it doesn't say, I don't see anything. It says maximize with respect to x2, this thing. That's it. The x1, you told me, we computed it here, done. x1 is done. So don't bring x1 anymore. But on the previous step, when you maximize with respect to x2, what values did we use for x1? All of the values of x1. So now, we found the x2, basically we found the maximum of this for all possible values of x1. So you know what you need to keep track? So in addition to maximizing this, to be able now to tell me what x2 is, what also can you need to tell me? Or what else do we need to keep track that will allow us to say an x2 is equal to that? So we maximize this for each x1, but we already know what x1 is. We computed it when we reached the root. So how should we find now the optimal x2? not for all x1s, but for that particular x1. So we need to find, so here we maximize with respect to x2 for every x1. So you will need to keep track of what is the optimal x2 for each x1 as a function. And then what you do is you go and plug in the x1 that you computed here, and that function will give you the optimal x2. You know, for x1 equal to 1, this is the optimal value of x2. For x1 equal to 3, this is the optimal value. Now we computed what the optimal x1 is when we reach the root, so we can go back to that function that tells us for each value of x1 what is the corresponding x2 that maximizes this, and plug in x1 and say x2 equal to that. So effectively, when we did elimination algorithms before, right, it was sort of from the leaves to the root done. We marginalize. Now, to be able to, it's okay, to find the maximum of this joint distribution, yes, it's a forward calculation from the leaves to the root, but to find the x's that do the job, we have to go backwards, right? So we now have to go and say, you know what? We know that the x2s that maximize this for each x1, but we know x1, so this will give me the proper x2. And then you go here and you say, you know what? To do this maximization, I need to know x1 and x2, but we already know x1 and x2, so that will give us the optimal x3. So we need to backtrack optimal x4, x5, x6 here is evident, so nothing to worry. So we need to backtrace this and find the optimal path. You notice in between, right, when you do these maximizations, there are multiple solutions. For example, when I maximize this, right, there are many solutions for different values of x3 and x2. If you pick up, let's say here, some value of x5, here's some value of x4, here's some value of x3, there's some value of x1, and you connect them together, that is not going to make an optimal path for the joint distribution. All right, so there are infinite paths, and you need to select the optimal path by going backwards. Later on, we will see that, so what we described is actually very general, but the implementation of this, the little algorithm that does this for hidden Markov models, is called the Viterbi algorithm, which is most probably one of the most famous algorithms in computer science, okay? It's used everywhere, okay? So this is a very useful problem, okay? And you can appreciate basically that now, yes, we go forward, we go from the leaves to the root basically to find the maximum, but to find the x that leads to that maximum, we have to go backwards. So there's a forward calculation, there's a backward calculation. Similarly, what we did with the sum product algorithm with sending messages forward and backward, basically, to be able to compute marginals and things like that. All right, so the algorithm is basically, we just discussed it, all right, so it looks, the initialization and the evidence is exactly the same algorithm that you use actually this is the algorithm that we use for the elimination, you know, but here, I call this, I suppose, I hope is not a typo, all right? I mean, I suppose Max-Summ, you know, map estimates for posteriors, but here maybe this for the general distribution would be the max eliminate algorithm. So anyways, we initialize, let's say we have a directed graph, we initialize all the potentials, we put them on active list, we introduce evidence potentials the way we did before, and now we have to do the updates, all right? And the updates are basically what I described with a particular example. You pick up a given elimination order. Now you're at node I. You find all the potentials that are involving node I. And then what you do is you maximize with respect to xi. All right? And once you maximize with respect to xi and you call this new potential, you will put this new potential on the active list. Okay, these are the remaining nodes from the elimination click, and then you keep proceeding until basically you reach the root, and whatever number you get when you maximize with respect to the root node will be the maximum of the joint distribution. Now, it is not shown here, right? But if you are going to keep track of the axis, if you want to keep track of the axis that do the maximization jointly, what you will need to do is here, all right, figure out, so here you maximize with respect to xi, all right? So you will need to figure out, there are several arguments here, nodes, right, that you compute for different, there are, these variables here are not eliminated that you see, okay? So for all possible values of this, you need to keep track what is the maximizing value xi, okay? And then when you reach eventually the root and you calculate the x root node that maximizes the final potential that you get, then you go backwards and you can calculate the remaining of the x's. So this is not shown in this algorithm, but basically what I described. All right. So actually the calculations look, and the messages, I mean, if you think of this as a message passing algorithm, it looks identical to what we have done for the, the product sum algorithm. The only difference, except of summations, we now have maximization arguments, all right? So what is shown here is basically when you are done and you have reached the root, all right? So when you have reached the root, at the root you have an evidence potential, and all the messages coming from the children of the root to the root, all right? And then what you need to do, the only argument here is xf, and then you need to maximize with xf, all right? So that will give you the argument, what is the, the node, what's the value of the root node that does the maximization, and then what you have to do is, you have to go backwards with this distribute command that you see here to actually backtrack and figure out what are the other x's that jointly will maximize the joint distribution. Okay, so actually this is how the backtracking is going to work, right? So if you look at the message, an arbitrary node j sends to I, it's exactly what we have looked with the elimination algorithm before. This is the evidence potential. This is the pair potential, xi, xj, and these are all the messages that go to node j except I. So basically the j sends to I its local evidence, this joint potential, and all the messages arriving to j except from node I, but then instead of summing xj, you're maximizing xj. Okay? And look now what else I need to keep track. I need to keep track the xj, all right? So we find the maximum here, so we compute the xj that maximizes this, all right? But we need to find this as a function of xi. Notice you sent a message from j to I, right? You maximize with respect to xj, but you need to do this maximization for all values of xi. All right? So effectively what you need to keep track is, you have to keep track of a function that gives you the optimal xj for each value of xi. So imagine you start sending messages all the way to the root. When you reach the root, will you be able to know what this value is of x at the root? You remember the big picture we had on node 1 was basically the only node left when we did the optimization of the root. So we will know what this is, and this then will give us the optimal values of the nodes that are children of x, and then we will use this to go one step further down and one step further down, and we will be able to compute basically all the x's up to the leaps. The point is, right, you calculate the xj's will maximize this for all values of xi, right? And you need to keep track not only of what that maximal value is, because you will need it to do this message passing on this max product algorithm, but also you will need to keep values of the optimal xj's for each possible values of xi. You will need this until you reach the root. This is what this bullet says, because at the root you will know what xi is, and then you can backtrack and compute all the other x's. All right? Again, you have to do this because if you start selecting randomly some of the xj's that maximize this for whatever xi, you're not going to get a consistent solution, basically, so you get the wrong solution. And if I can show you this, actually, there's a graph somewhere. I'm going to come back to this, right? So if you think of, if you have, let's say, Markov chain and x1, let's say, can take 3 values, x2 can take 3 values, etc., xn plus 1. So this is one possible path. This is another possible path, right? But the way that you will figure out the optimal path is you will reach basically the root node. You will find what is the optimal value of the root node. And then basically from there, you will find what is the corresponding previous value for that value of the root node. And from there, what's the corresponding value of xn, and then xn minus 1. So basically, you will find which is the consistent path that gives you maximization of the joint. Again, this is one of these little things, right, that you need sort of to program to see it in action, all right? And what is interesting here is, again, the algorithm gives you the impression to start with that you can maximize it by a forward calculation, but to figure out the argument, the axis that maximize jointly the joint, you have to do a backwards algorithm as well, and that's what this is all about. All right. Let me see, and I'm going to pick it up from where we left it. So basically, this is, if you think about it, if you have a program that from the previous homeworks, let's say, and I'm not sure, maybe this will come in the next homework, but if you have a program that does the marginalization of the spectrum xj, you can easily see here, you remove the summation, you make it a max, and you're in business. Basically, the same algorithm can do the job with almost minor modifications. Okay? All right, but remember that you will have to add this backtrack step as well. All right. Now, so what we discuss is this max product algorithm, and the most popular version actually of it is not it's not called the max product, it's called a Max-Summ, where rather than working with messages the way we have seen it before, you work with log messages. So all the multiplications then become additions, and the algorithm becomes Max-Summ. And the reason that this is working is basically, if you try to maximize the joint of p of x with respect to x, and you take the log, this is the same as maximizing with respect to x, the log of p of x. Which means, if I define h to be the logs of the messages, all right, if I define h to be the logs of the messages, this is how the algorithm looks like, okay? So the log of the message from j to I, for all possible values of xi, is, before you remember, we had all the product of the incoming messages from all the neighbors k of j. Now we have a summation of these log messages, and the log of the local evidence and of the potential for this pair potential. Okay, so the algorithm is called not max product we had before, so now it's a Max-Summ algorithm. Okay, minor change, but obviously this algorithm with logs, it is way more useful because if you have if we go back, right, and this is a general problem, has nothing to do with this max product algorithm. Imagine that you have a big graph and you keep multiplying with messages, okay? Eventually, lots of these messages will be extremely small, and basically these messages will be uninformative, and you'll be getting a lot of zeros, 10 to the minus 50, 10 to the minus 30, etc., and you get in trouble. So this is an underflow problem that, in part, using logs, right, and doing these summations, avoids this problem. And even then, there is a trick that you can find practically if you search, even in MATLAB, you know, on their toolbox, everywhere on Kevin Murphy's MATLAB toolbox, or any Python programs you find where they use this message passing algorithm, they sort of course they use logs for the messages, right? But also they do an additional trick that I wanted to show you, because if you program without this trick, you're not going to be able to actually do large-scale programs. So here's where the trick is. So the messages, this is what we had before, and I'm writing this in the context of the eliminating xj. So you can have the max operator there, it's exactly the same thing. So we use log messages, all right? And so summation xj of this times that, and because these are log messages, I can write this, let me see, this will become a summation, all right? And if I put a log outside, because this is a log message, I'm going to have an exponential inside, okay? So we need, this looks extremely complex, right? Because we have to find the log of a summation. And by the way, log of a summation is very typical in many algorithms in machine learning, okay? Unfortunately, you cannot take this log and put it inside. So log of the summation in xj. So we write those two terms as exponential of the log of size. This is what I have. And because I put the exponential outside, so here I have a summation, all right? So you take all of this and you call it Lij. All right, this is what I have, exponential of Lij. And then you find out the maximum, find the z that maximizes, that is the maximum basically from all the Lij's. So you pull this outside, and then what you're left is exponential of Lij minus Liz. Okay? And this is how basically you have to implement the log messages when you write your computer program. You can play with this and convince yourself actually that this avoids underflow issues the way it is here. Okay? So, so remember sort of this little algorithmic step, and actually if you see it in computer programs, know that it's nothing strange. Basically it comes by the algebra that is simple. Okay. Can you do the Max-Summ algorithm on factor graphs? The answer is, of course, you can do anything you want to. And if we use, again, log messages, the boundary conditions basically, if x is, let's say, in the leaf node, the message that we send to the first factor is 0. You remember when we did last lecture, this message was how much equal to? 1, but now it's a log message, so it's 0. And if the first node is a factor on the leaf, then the message is the log of the potential of the factor. And this is the messages basically that we were working on the last lecture. If you want to send a message from a factor to a node, you take the factor potential, you take all the messages that arrive from all the neighbors of the factor except x, that arrive to the factor, you multiply them, and then you basically eliminate, you integrate out x1 to xn, all the nodes that are involved in the factor except the node x, okay? So, and similarly, if you wanted to find the message a node sends to the factor, it's the message that all the neighbor factors to the node sent to that node, except of course the factor fs. So you multiply all the incoming messages and you forward them to the factor fs. So if you take this and exchange the summations for the max operator, and you want to do the Max-Summ algorithm factor graphs, very trivial. The message from a factor to node x is the maximum of this. All right. Notice we're going to have a log of this and a summation here. So obviously, when I write this equation, the implication is that now these mu's are logs of the actual messages, right? They're logs. That's why you see here the product became a summation, and again, from a node to factor, you notice the product becomes also a summation, and the rest is basically history. When you reach the root node, you'll be able to find the value of x that does the maximization of all the summation of all the messages coming from below, and then you need to do backtracking from the root back all the way to the lifts to figure out what are the x's that maximize the joint distribution. So again, if you have an implementation of the sum product algorithm of factor graphs, you can transform this to a Max-Summ algorithm by changing the definitions of the sum and exchanging sums with the max operator. And if you're not already doing this, and you have to do this in your homework, try basically not to use messages we know, use log messages to see how things will look like. All right. This is basically is the same thing we just discussed on a simple chain as an example. All right. So all the messages that you see on this plot, I think this is an application of a graph we had on an earlier lecture, but now the way I have it, all the messages are basically for the for calculating this maximum of the distribution, and they are logs. So apart from that, they are the same. So the message from xn to this factor, all right, is the same as the message from this factor to this node. So whatever, because this is a chain, whatever message this node receives from this factor sends it forward to the next factor. And if you want to find the message, let's see, this is the message from the factor n-1 n. What is that? So this is, we want to compute this message here, right? This is what we want to compute. So this message, you know what it is this factor times the incoming message. So what we're going to do is we're going to take the ArgMax with respect to xn minus 1. In the earliest algorithms, we were summing xn minus 1. Rather than having the potential, we now have the log potential plus the incoming message, which is here. Okay, that's basically the two relations that you need to be able to propagate messages for this Max-Summ algorithm. Now, can you tell me, so to be able to do the backtracking, can you tell me what function are you going to need to keep track here? So here you compute the maximum of this and you set it to this message. But we also need to keep track of xn minus 1 for what? For every value of xn. You see that? We will need to figure out, we need to do this maximization for all possible values of xn. So we're going to need to find the optimal xn minus 1 as a function of xn. And the idea is, if we have all these functions and we reach the root, we will know what the x root is, and then we can use all of these label functions to go backwards to figure out all the previous x's. Okay? So basically, what I call here, I call this function phi. So when I find, let's say, here the maximum of this expression that you see here, it effectively at the same time it gives me the optimal, the maximum, the maximizing xn minus 1, but as a function of xn. Okay? We will not know xn, all right? So in the next step, we will also need to keep track of xn as a function of xn plus 1. And xn plus 1 is a function of xn plus 2 until we reach the root node where we will be able to figure out what the root value is and then go backwards. All right. So before, and if I have time to tell you about the junction tree algorithm, I wanted to just put very few slides for this sort of historical algorithm of belief propagation on directed graphs without loops. This most of this work is in a little very important book by Perl on probabilistic reasoning in intelligent systems. You may even be able to find this book online. And so the derivation is actually, if somebody knows this algorithm based on elimination, this sum product algorithm that we developed, so this comes out to be a sub-case. So in some sense, I'm going to derive it a little bit different for directed graphs, but you can see that the algorithm actually looks the same, okay? So, this is our directed graph, okay? So we are looking at node X. U's are the parents of X, Y's are the children of X, and etc. And think of this as a tree, okay? So basically, if you remove the directionality of the edges, basically you get an undirected tree with single path, basically from one node to any other node. So let's call the evidence here E. There are three key ideas, basically, to be able to understand this idea of belief propagation, but again, it's the same algorithm practically with what we have seen. So we are looking at X, and so the idea one is that the probability of X, this is sort of the marginal of X, this is what we have done up to now, combines information from upstream and downstream. So basically it combines evidence propagating from upstairs and evidence propagating from downstairs, okay? And the idea that I can split the evidence on upstream and downstream has to do with the fact that X disseparates the evidence from up and down. You can see this, right? To go, if you have evidence there and evidence down there, and you have to pass through X, X basically blocks that, so it separates the evidence from upstream and downstream. So if you want to compute the probability of X given the evidence, let's say this is our problem. This is basically the belief, all right, that we want to compute about X. So I can write this as the joint of X and E divided by the probability of the evidence. Because the X disseparates the evidence plus and minus. Plus is the evidence up there, minus the evidence down from X. I can write this EX plus and EX minus, and this is not important for X, so we don't care. So I can write this as the probability of EX minus given X and EX plus, and the probability of X given EX plus, all right? And because X disseparates, all right, I don't need to keep the EX plus here. So this belief can be written as the probability coming from upstream evidence, and this term that is the probability coming from downstream evidence. Okay? So this is basically using Bayes' rule and the fact that we have a disseparation here that I used in this equation. It allows me to write the belief, or the in this case is conditional on the evidence, right? But you can think of the calculations we were doing earlier for marginals, that they were sort of the same. So think of this as a message coming from upstream times a message coming from downstream. Isn't it what we did when we computed marginals, right? Is the product of the two messages. But now you notice these things basically were derived from Bayes' rule. I'm not going to elaborate. If anybody's interested, we can philosophize on this, but you can call this, you can put a prior on X, right? And a prior naming, and this is the likelihood that is coming from downstream. But right now, we have to compute this term that is information coming from upstream, and this term that comes from downstream. So that's idea one, right? That we can combine upstream and downstream information to find the probability of X. Idea two, that the idea two is that this message, as we know, can be computed by local message passing algorithms, which we have seen, okay? And the last idea, which also we have discussed it, don't ever send to a node any message the node sent to you. That's it. So I am going to give you the equations, and I want you to actually study them because they have a historical significance. So we define the belief of the node X to be the conditional probability of X given the evidence, and we just stated this as the information coming, so let me see what the definition here, coming from downstream. So this term lambda comes from the children. This is what we derive from Bayes' rule, and this is the information coming from the parents, okay? So I'm going to give you the message passing algorithm that tells you what lambda is and what pi is based on what we have done, all right? So we need the information coming from the children of X to X. Looking at this graph, can you tell me with message passing algorithms, what is the information that comes from the children to X? And again, symbols, they are on this slide, but tell me with words. Basically, I want to find all the information that comes from downstream to X, and I want to do this through messages that the children of X send to X. So what is lambda of X? Is the product of what? Is the product of all the messages the children of X send to X. Isn't it the way we have done it before too, with message passing? All right. So there's nothing there. Lambda of X is the product of all the messages these Y's, the children of X, all right, send to X, okay? Let's now calculate the information that comes from upstream, which is this, the pi of X. So what information comes from upstream evidence? And here's the calculation, which is actually literally the same as what we have done up to now. You know what? I showed you the equations actually a few minutes ago, talking about the max product or Max-Summ algorithm. So this is the probability of X given its parents, because this is a directed graph. And this is all the messages the parents of X send to X. And then what do we do? To find the information X receives, we integrate out all the parents. This is exactly identical to message passing that we have seen before, okay? All right. So basically, we have an equation to calculate the belief of X by taking the product of upstream and downstream evidence propagated to X. But obviously, if you're going to calculate the messages, let's say the children of X sent to X, to be able to do this, you're going to have to compute the information that X sends to its children, and also you're going to have to compute the information X sends to its parents, right? You're not going to be able to calculate these messages alone, so you have to calculate those messages as well. So This is what you see here. Look graphically, this is the message the X sends to its parent UI. So without the equation, can you just, forget it, don't look at the equations. Look at this picture. Can you tell me what message X sends to, let's say, to UI? What will it send to UI? What information X will send to UI? I mean, we did lots of examples, right, with message passing. So if I'm asking what X sends to UI, so which is this message, what will it do? You're going to send all the messages you receive from your children, and I put all of them together as lambda of X because you remember lambda of X, it was the product of all the messages from the kids, okay? And then you're going to have to send all the messages you receive from your other parents except parent UI, because you're going to send a message from X to UI that you also receive from U1 and U2, etc. So what you need to do is, again, the potential, this is like the click potential there, X given its parents, times all the messages you receive from all the other parents. You notice K not equal to I. And then, of course, what you need to do is integrate X out. And, of course, in this term, you're going to have to integrate all the other parents out, right? And what you get is a message that depends only on UI. It's exactly the same as before. So with messages, the way we have done it with message passing, it looks very clean. But this is an important algorithm because it was developed in 1983, before people were even talking about machine learning in any serious extent, right? And so this algorithm has been extremely influential in theory and in practice. Extremely influential, okay? And similarly, if you want to find the message X sends to, let's say, to one of its kids, what you will do is you will multiply the messages that the other children send to X. So you will send them to children J. So you notice K not equal to J. But also you will send all the messages the parents of X send to X, which is what we had here with all the U's integrated out. Now, you notice here it says the product of all the messages coming from all the kids but J. So actually, if you multiply with the message coming from the children J as well and divide, you can write the message that you send to a children J as the belief of the node X divided by the message that the children J sends to you. So that way you don't double count the message that J sends you. You remember when you write this, right, it will involve this times the message that children J sends to X, which we don't want to. We're not going to send to J what it sent to us, so we divide it by it. And this algorithm where you have this belief of X divided by this message, has sort of some algorithmic advantages here and there, and in some of the implementations of this message passing algorithm, you may see this type of division. So rather than saying, do this multiplication for K different to J, this is another way of writing it, right? So the belief of X divided by the message that J sent to X. Am I giving you a headache already? A little bit? Yes? You said yes? Yes, all right. The slides are up on the web, actually. This I put them together today, all right? So they're up. Okay, they're typed, so you don't have to run just writing equations and K is different than J and all of this. You cannot duplicate this by hand. It takes lots of effort, okay? This is for professors who have nothing to do at night, to just do lots of typing of slides, okay? And Suvik helps me obviously this semester with the slides, and but in some sense, when I ask you to type your homework, there is a reason, right? When you type things, you look at them and you look again and again, you say, you know what, doesn't look right. And if it doesn't look right, it is not right. And you can only say that when you type them. When you do like that, everything looks bad, right? Good or bad, correct or not, it doesn't look good. But when you type it, if visually it doesn't look right, it's most probably not right. Okay. Any questions? Nope. All right. So I'm saying no because 132. So let me do the following thing. I am going to discuss the junction tree algorithm, and I'm going to give you sufficient time actually to go through this today as an introduction, and I'm going to give you formally the structure of the algorithm when we go back to it on Tuesday. For reference, by the way, of the lecture today and also the lecture for Tuesday, one of the chapters of Michael Jordan's book on junction trees is basically the best read for the subject. Okay, very elementary, but sort of addresses everything very nicely. All right. So let's consider, again, I'm going to do this through an example to motivate what the algorithm is. So let's assume that we have a directed graph that looks like this, all right? Obviously, this is not a tree, right? You can see it. I mean, if this there was not there, you can claim this is a tree, but this is not a tree. So, we have to see how this new algorithm, the junction tree algorithm, will help us to calculate things. All right, so what we're going to need is, I'm going to take you through the process. Okay, so I notice here, so I'm going to convert this to a non-directed graph, and as we have seen before, the first step is to moralize. Basically, an X5 has two parents, so we moralize and we get a non-directed graph that looks like that. All right. Now we are going to select an elimination order of this graph, and we're going to keep track basically of the elimination clicks. And when we finish, we're going to try by keeping track of the elimination tricks to create a tree that has factors that consist of the click potentials. All right. So in other ways, when we eliminate, we have seen this on purely graphical, with purely graphical interpretation, we create elimination clicks. So this elimination clicks will define basically new nodes on the junction tree that are going basically to contain the functions, the factors affiliated with those elimination clicks. We will see this on this particular example. All right. So before we do the elimination for this, so this is what we got, right? I'm going to do one more step that somehow we omitted on the previous slide, and I'm going to connect nodes x2 and x3. This is what I am saying. I'm calling it, I'm going to triangulate the graph. And can you guess potentially why basically I need to triangulate the graph? I told you that at the end of the day we're going to keep track of elimination clicks. So why do you need, here I had 4 nodes connected together. Why do I need to triangulate the graph? What potentially benefit may exist there? Well, if I kept these 4 nodes together, what is the, this is a big potential because it involves 4 nodes, right? So we need sort of to reduce that to 3 nodes. But beyond that, there is a fundamental property that I will show you when we complete this, that without triangulating it, you're not going to be able to make the junction tree algorithm to work. So, remind me to tell you when we reach the end of this example, all right? So, for first reason is we want to reduce the size of this click, but there is another important aspect that we will see when the algorithm finishes, okay? So, we eliminate node 1. What is the click, the first elimination click form is 1, 2, 3, all right? We write it down, C1, 1, 2, 3, okay? Now we're going to eliminate, let's see what is the next node we want to eliminate, node 2, okay? That's our order. So the next elimination click is 2, 3, and 4, 2, 3, and 4. This is what we left. The next elimination click is 3, 4, and 5, so we will eliminate node 3. So 3, 4, and 5. The next elimination will be for node 4. So the next click will be 4 and 5. And then I have 5, so the next click is node 5. And what I'm going to do is, so we kept track of all these clicks, and I'm going to get rid of the clicks that are a subset of other maximal clicks. All right? So we're only going to keep track of these maximal clicks, 1, 2, 3, 2, 3, 4, and 3, 4, 5. All right. So now I am going to consider this as nodes in one graph. All right. So this is click 1, 2, 3. So the nodes, the variables that are contained in node C1 are x1, x2, x3. Variables x2, x3, x4, x3, x4, x5. So what I'm going to do is I am going to pay attention to here. You notice I am connecting all of this together, but this is not really a tree. And so we need to come up with a tree that involves this click graph, all right? And that click, we're going to come up with it as follows. We're going to look at this connection here. How many common nodes those two clicks have? 2. Look at this. How many common nodes they have? 2. How about these two clicks? Where is 1? 3, yes. So only 1. So we're going to design a tree that has maximal weight assigned to the edges, and weight is accounted by how many common nodes are shared between these maximal clicks. And obviously that tree, you will agree with me, will be C1, C2, C3, and there is this tree, because these nodes are 2 and 2, so this has the maximal weight, right? And this is what we call the junction tree. Okay? So this node is just to, I'm not going to use it, this is a tree, right? So we went from this directed graph to a tree that involves potentials defined using these maximal clicks, basically, all right? Obviously, the fact here that I accounted on how many common nodes we have in the edges indicates that potentially there are more than one junction tree that may do the job, okay? So in this case, obviously, this is the obvious solution, okay? All right. And this is the important property that, we will elaborate this on Tuesday as well, but the reason we triangulate it is the following. Look at clicks C1 and C3. Node X3 is common to clicks C1 and C3. To be able to have consistency in the calculations, consistency between the clicks, and in the way we're going to be computing marginals, if X3 belongs to C1 and C3, it also has to belong to any other click from C1 to C3 via this tree. So if X3 was not there, basically we would not be able to propagate messages from C1 to C2 to C3, because how are you going to propagate messages about X3 when this is not a function of X3? All right? So this property is called the running intersection property. Okay? So if a variable is common to two clicks, that is, for example, C1 and C3, has to be also part of any intermediate click from C1 to C3. Okay? Now again, I mentioned that this is essential for maintaining consistency when you calculate marginals on this graph. I'm going to actually discuss this in detail on Tuesday, right? But right now, this is basically how our junction tree looks like. All right, and before we complete, it's not that you need it, but it's sort of part of the way that people look at these algorithms. In addition to these click potentials, they define the separators, which are basically the nodes that are common between these maximum clicks. All right? So the common nodes here are x2, x3, the common nodes there are x3, x4. So when we do message passing from C1 to C2, can you guess the messages that we will send will contain information on what variables? Let's say if C1 is going to send a message to C2, that will be information that will update what variables? Only the variables that are involved in the separator. I mean, you're not going to go and send a message about x1 when this doesn't depend on x1. All right? Okay, so this is what we have. And now, what potentials you assign to psi1, psi2, psi3 is basically like if you had this graph, right? You can make your own assignment of potentials that involve variables x1, x2, x3 here, potentials that involve x2, x3, x4, and similarly here x3, x4, x5. You basically have choices if you start from a directed graph of how you do this assignment, but effectively whatever factorization you have here, you can transform this to psi1, psi2, psi3 defined over these maximum clicks. All right? And the rest, you know what, is history. You can use this message passing algorithm that we have seen for trees, and now you can do this in junction trees, even though your original problem had nothing to do with trees. So how do you do this? You can compute a message this click sends to from 1 to 2, and how do you compute? Is take the potential of click C1, and then what do? You integrate x1 out. There's no incoming message from anywhere, right? So this is like the root node. There is no incoming message. So this is n to 1 to 2. Let me see if there's another picture. If we look at the message from 2 to 1, obviously you're going to take this potential, all right? But also there is an incoming message from C3 to C2, which is that. And then you have to integrate variables that don't belong in the separator, and that's variable x4, so you integrate x4 out. Okay? And how do you compute, so I can finish, when you finish, if you are interested, let's say, to compute the marginals corresponding of the variables x1, x2, x3 corresponding to this click, what you do is, this is the local potential psi1 times the message that arrives to C1 from C2, the neighbors. How do you compute the marginal of x2, x3, x4? Take the local potential times the message 1 sends to 2, take the message the 3 sends to 2, and you're done. All right? So this algorithm actually works on all sorts of graphs. If it works actually, it comes out to be exact. People are using it even when you have graphs with loops. And as already we discussed, the algorithm is called the Loopy belief propagation algorithm. If you have loops, you basically have to, there is no such a thing as get all the messages from the neighbors and then propagate them, right? Because you have loops, so what you need is initialize all these messages to maybe 1 or some arbitrary values. So any node can start sending messages to all the other nodes, and then you can apply your classical message passing. So if you have loops, the junction tree algorithm may work, and a lot of time works, but if you search the literature, there are some very standard toy problems where it fails drastically and it doesn't work at all. Okay? But there's no proofs why it works when it works, but it actually works, and it works for arbitrary graphs, and you know, and you can make it actually to work exactly. Okay? So 146. The slides are up. I think there is another example. Read it, and maybe read Jordan's chapter on the junction tree algorithm. So when we come back on Tuesday, we can finish these general inference algorithms on one lecture. So tomorrow, Sulik will discuss. Don't leave. Okay? Just so we'll discuss about the homework, and hopefully we can at least post on the web one or two problems by tomorrow, so we know what we're talking. All right, that's all. If anybody, because nobody comes to visit me, if anybody wants to discuss lectures, etc., you can stop by when I'm there. Usually late afternoon is the best time, okay? So.